In this module, we will discuss sound and hearing. Here we will tackle when we have source and listener moves. Human voice is a complex mechanism that is able to produce sound through the orchestrated play of various parts of the mouth. The air required to produce the air vibration, which is done using the lungs, then the power needed and articulation through your muscle in the face. Sound waves like this are a type of longitudinal waves that travel through air as the medium. So, in absence of air, then there would be no sound. So when you see a movie explosion in space, it is a movie physics. There is no sound in space explosion due to the absence of air molecules to propagate the vibration. The human hearing has a range between infrasonic to ultrasonic, and this usually varies with age. Some sounds will be less audible due to deterioration with age. Longitudinal waves in a three-dimensional space will have a spherical motion. Shown here is a singer where we imagine the sound waves as concentric circles as it propagates away from the source. We recall in the previous module the difference between transverse and longitudinal waves, that the transverse wave is described by the displacement of string. For longitudinal waves, it is described by the displacement of fluid, and for this case is the air molecules. This causes variation in pressure. Here we see the changes in pressure when particles are close or far apart. When particles are compressed, there is an increase in pressure, and this position is called the pressure antinode. When the particles are fewer or far apart from each other, there is a decrease in pressure, and this position is called the pressure node. The position of the pressure node is the position for the displacement antinode. So, we see. Here we see the graph of pressure and displacement function. Currently, we are familiar with the function for the position variation, and now we derive pressure. We recall our previous knowledge about pressure variation. If we consider the surface of the Earth is the position for the atmospheric pressure, then pressure P is the absolute pressure, the P0 is the atmospheric pressure, and the density times g times height as the gauge pressure. So, here we are to determine the gauge pressure. We see that gauge pressure is the gauge that varies from the normal atmospheric pressure, which is indicated by the dashed line. So we imagine a sound traveling through a pipe with a cross-section area S. Initially it is at position y1 with a length x. At a later position it is at y2, where it has expanded to a much greater volume and expanded to a length of x plus delta x. If y2 is greater than y1, then the volume has increased, thus pressure decreases. If y2 is less than y1, then the volume has decreased, thus pressure increases. If y2 is equal to y1, then no change in volume and pressure. The cylinder may be shifted to the left or right. With volume V equal to surface area times the change in x. Solve for the change in volume as surface area S and displacement function y of x and t. The cylinder may be shifted to the left or right. With volume V equation, solve for the change in volume as surface area S and displacement function y of x and t. We see the equation here. Here we relate that the rate of change of volume as delta x approaches 0. We re-express this as a partial derivative with respect to x as we take the surface area S constant, so it cancels out. We relate this to the bulk modulus property to obtain an expression for the pressure function. Rearranging the expression of the bulk modulus and substituting the expression of the derivative of volume, we see that the pressure function is equal to the amplitude times the bulk modulus, times k constant cosine of the angular frequency times t minus the wave number k times displacement x. Graphing both the pressure function and displacement function here, we see that the maximum length or maximum pressure is given as the amplitude times bulk modulus times wave number. This is what we call the maximum pressure when the cosine function is equal to 1. So for this condition to be satisfied, the term inside should be a multiple of pi. In music, sound is characterized into three properties: the intensity, pitch, and quality. These properties create a basis for how musicians are judged on how good they are. Sound intensity is the average power transferred per unit area. Mathematically, it is the average value of the pressure times wave speed function. Taking its average, which is simply 1/2, we get that it is equal to 1/2 times bulk modulus times wave frequency, times wave number, times amplitude squared. Here we have other expressions for intensity. The usage depends on the given information from a problem. You can use the following equations below to obtain the different expression for intensity. Here we have another form of expression for intensity as a function of power P. Here we can relate the distance and intensity. As you know, when we are farther from a sound source, the sound becomes less and less. Here intensity is a function of the distance denoted by r or radius. We see that because it is an inverse square, the farther a listener is, the less the intensity. In this scenario, the sound waves propagate spherically, producing two concentric circles viewed in a two-dimensional plane. So, there are two intensities based on the difference of distances, but the power remains the same. Equating the two expressions, the ratio of intensities is equal to the inverse of the distances squared. Decibel scale is the sound intensity level of a sound wave, which is defined as 10 times the logarithmic function of the ratio of the intensities. Here intensity I0 is a constant taken to be 10 to the power of -12 watts per meter squared. We can also obtain another expression for intensity as a function of the decibel level. Similarly, we can compare two different decibel levels by taking its difference, which is just the ratio of the logarithmic intensities. We can also form an equation in terms of the power by using the expression obtained earlier. We see that it is also the ratio of the logarithmic function. Beats occur when waves with equal amplitude meet or converge but with slightly different frequencies, as shown in the figure. The equation for beat is written here. Pitch refers to the rate of sound waves you are sending and which we sense as high or low voices. As we experience when we move towards or away from a sound source, the strength of sound varies. Here we see that when a source is moving in a certain direction, the shape of the wave is deformed. It concentric oblongs, and with that the front and back wavelength is altered. The front wavelength labeled as lambda A appears shorter compared to wavelength at the back. The frequency of the source remains constant as the source moves, and the speed of the wave in air is also constant. So, here the factor that obviously alters the wavelength here is the speed of the source. Similarly, the speed of the listener also alters its perceived frequency. When a source of sound and the listener are in motion relative to each other, the frequency of the sound heard by the listener is different to that of the source. This phenomenon is called the Doppler effect. Here we have a stationary listener and a stationary source. The propagation of the wave is symmetrical with equal wavelengths on all sides. We see that the sound wave travels with a wave speed v on all sides also. Here the frequency heard by the listener is equivalent with that of the source. Here we have a scenario where the source is stationary but the listener is moving towards the source. Logically, we expect that the sound heard would be louder. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air plus speed of the listener over the speed of sound in air times frequency of the source. So, we see that the ratio factor would result in a value greater than 1 and would result in a frequency greater than the source. Here we have a scenario where the source is stationary but the listener is moving away from the source. Logically, we expect that the sound heard would be lesser. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air minus speed of the listener over the speed of sound in air times frequency of the source. So, we see that the ratio factor would result in a value less than 1 and would result in a frequency lesser than the source. Here we have a scenario where the listener is stationary but the source is moving towards the listener. Logically, we expect that the sound heard would be louder. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air over the speed of sound in air minus the speed of the source times frequency of the source. So, we see that the ratio factor would result in a value greater than 1 and would result in a frequency greater than the source. Here we have a scenario where the listener is stationary but the source is moving away from the listener. Logically, we expect that the sound heard would be lesser. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air over the speed of sound in air minus the speed of the source times frequency of the source. So, we see that the ratio factor would result in a value lesser than 1 and would result in a frequency lesser than the source. Here we have a scenario where the listener is moving towards the source and the source is moving away from the listener. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air plus the speed of the listener over the speed of sound in air plus the speed of the source times frequency of the source. Here the frequency heard by the listener depends on the relative speed of the listener and source. Here we have a scenario where the listener is moving away from the source and the source is moving towards the listener. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air minus the speed of listener over the speed of sound in air minus the speed of the source times frequency of the source. Here the frequency heard by the listener depends on the relative speed of the listener and source. Here we have a scenario where the listener and source are moving towards each other. Experience tells us that the sound we would hear would be loud. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air plus the speed of the listener over the speed of sound in air minus the speed of the source times frequency of the source. Here the frequency heard by the listener is expected to be quite large. Here we have a scenario where the listener and source are moving away from each other. The formulation for the frequency heard by the listener is given as ratio of the speed of sound in air minus the speed of listener over the speed of sound in air plus the speed of the source times frequency of the source. Here we expect that the frequency heard by the listener would be the least compared to other scenarios. Here we have the summary of the equations to be used when determining the frequencies based on the relative position of the source and listener. When the source travels faster than the speed of sound, it is called supersonic. Doppler effects no longer describe this situation. Here the speed of the source is faster than the speed of sound in air. The event is known as breaking the sound barrier. You can demonstrate this by cracking a whip, where you will hear a loud snap which indicates that the tip of the whip has moved faster than the sound of a wave. Here we look closely at the two different events where a plane sound wave before and during the breaking of the sound barrier. At a later point S2, the wave front forms a cone shape as outlined by the two lines that intersect at the tip of the plane. Here we can write an expression for the relationship between the wave speed and the speed of the source or plane. Using a sine function, we get that it is the ratio of the length d and radius r. We see that at the event of where the plane breaks the sound barrier, the sine angle of alpha is equal to the speed of sound in air over the speed of the source. Here we have an example. A police car's siren emits a sinusoidal wave with frequency 300 Hz. The speed of sound is 340 meters per second and the air is still. Letter A, find the wavelength of the waves if the siren is at rest. Letter B, find the wavelengths of the waves in front of and behind the siren if it is moving at 30 meters per second. First we draw the problem. The first case, the siren is at rest. We see that the wave front has a symmetrical shape and we expect that the wavelength is the same at all sides. The second case, find the wave front appears deformed as it moves at a speed. We expect that the wavelength is different at the front and at the back. So for a speed of a source at rest, the sound radiates symmetrically with a speed of sound equal to 340 meters per second. Recall the equation of wavelength, which can be expressed as the speed of sound over the frequency of the source. The calculation shows that the wavelength is equal to about 1.13 meters for a source at rest. For a source moving at a speed 30 meters per second, we see that the wavelength is different at the front and at the back. We recall the expression for the wavelengths for the front and at the back. For the front, we see that the length is shorter due to the same direction of the source and the wave front. Substituting the values, we get that it is about 1.03 meters. Now at the back, we see that the wavelength is expanded due to the opposite direction of the wave front and the source. We get that it is about 1.23 meters at the back of a moving source. Here we have an example. If a listener is at rest and the siren is moving away from the listener at a speed of 30 meters per second, what frequency does the listener hear? First we draw the problem. So, we see that the frequency will be reduced since the source is moving away. So we see that this is an example that fits the case 5 where the listener is stationary and the source is moving away, and the appropriate equation is shown here. We then substitute the values needed for this case where the source is moving away from a stationary listener. We get that the frequency heard by the listener is about 276 Hz. This is less than the source, and it makes sense since the source is moving away. The police car is moving toward a warehouse. At what frequency does the driver hear reflected from the warehouse? Note that the frequency of the siren is 300 Hz and the speed of the car is 30 meters per second. For case A, the car emits a siren with a frequency of 300 Hz. For this case, the building acts as the listener that is stationary. What happens after is that the sound is reflected from the building and it is heard by the car, which will act as a listener for case B. This phenomenon is called an echo, where sound reflects from a surface. First we solve the frequency reflected on the building. So for case A, this is identical to the scenario that for the source that is moving towards the listener. So, we use the equation which will give us a larger frequency compared to the source. We get that the value of the frequency for the listener is around 329 Hz. This will become the frequency of the source later when this wave is reflected back towards the car as the listener. For this case, we have the building acting as the source with a frequency of 329 Hz and the car will act as the listener. This is a case 2 type scenario, so we use the equation that describes it. Substituting the values, we get that it is around 358 Hz, which is comparable to its original frequency produced by the siren. This case shows that 2 or more Doppler effects occur in a scenario which we observe, in which we produce sound waves in buildings with sound reflective surfaces like that of caves. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at @dieslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.